grants when when I have a co-professor.
So, and how many times, I'm just curious about like fundraising for a lab, how many times you have to apply for grants within the year?
Oh gosh, as many as possible. Like, so a lot of people, like the NIH, for example, you can submit to them 3 times a year in any given like type of call. So most people like that I know never miss a deadline. The NSF, they have, it's hard to say, like, so they don't have a deadline, supposedly. But yeah, I mean, so I try to, like, at any given moment, I try to have at least 2 or even better 3 grants that are like submitted but not yet. Sorry, I'm trying to close my windows that might make noise. So I try to have 2 or even better 3 grants that are submitted but not yet decided on yet. So that ends up being like 7 a year-ish.
Okay, because I'm just thinking about, okay, when you have, so this is kind of a founder's dilemma in the startup world, because usually a founder is just raising money. And I'm thinking, okay, if this is similar for like a researcher, it's time consuming and probably not the best thing to do when you're like the top researcher in your field. Just this. Okay, hey Steph.
Hi.
I've been through your slides, and I honestly have to say this is so interesting. It's much personally, it's much better than the last presentation, because it's for me it's more like personal, like energy, and then one slide specifically is how can we use photosynthesis for energy storage, and this is like, I don't know, it's just very interesting, and I'm very keen into the questions and what all the other people will say, and probably their opinion, and also what you have to say on the specific slides. There's one black slide. It's slide 23.
Oh yeah, that's the end of the talk.
Okay.
Everything after that is just in case people ask anything that I need to pull up an extra slide for,
Malte, I'm sorry. I just have Thomas on the other line. He wants to know, with which account are you logged into this Zoom meeting?
With the one that he sent me, like Thomas at Delody.
Thomas at Delody, he says.
Yeah. But why?
Oh, Malte, you have noise in the back.
You're like working in the kitchen or something.
Sorry.
Yeah,
yeah, actually, that's the kitchen. It's over there. Sorry. It's not that. Is Leah joining us?
Malte, I'm gonna add the questions into the doc as we did last time, right? I'm going off camera. Enjoy.
Okay. Thanks. Okay, so Thomas is here, Adrian is here, Liam is here. Who is here? Hello. Thomas, could it be possible that you have to let them in?
No, you just have to click on it and then they kind of come in by themselves. I just did that actually.
Okay.
It works by itself.
Okay, so good, perfect. Okay, hey Nicholas. Hello Uwe. So we're gonna wait till, let's say, 3 something, and then we're gonna start with Anne's talk. And I also will say a few words about NextNess, what it's all about. And hopefully you will enjoy that conversation. For everyone who is not here or who's here for the first time, I'm very happy to see you. Hello again. Hi, Chai. So, actually, last time I tried to play some music till we're waiting, but to be honest, I don't know how to play music through Zoom if I have headphones in. So everything you will get is like noises from the back and kitchen noises. So hope everyone is okay. Maybe thumbs up if you're doing good. Let's. Hello, Keith.
Good afternoon.
Good afternoon. Where are you all coming from?
Bern, Switzerland.
Oh, Bern, Switzerland. So good afternoon as well. I guess most of the people are from the US here. Like Nicholas, Uwe, where are you from?
From Germany.
Germany. Hello. Adrian,
I'm from
where
Canada.
Are you from? Oh, Canada. Where from Canada?
Vancouver Island, which is close to Vancouver.
Oh, nice. I used to live in Tofino for a couple of months.
Oh, wow. Oh, yeah, I'm close to there.
Yeah, just for surfing, but yeah, it was fun.
Living in Canada.
I was there this summer.
Yeah, pretty much the summer, yeah. And I spent the winter in Montreal. It was kind of freezing there, but yeah.
Yeah, I've heard.
Hi, Tillman.
And I love spending time on Vancouver Island and spent my honeymoon on a boat 10 days in the Desolation Sound area. So I also very much appreciate.
Yeah, it's pretty much like swimming with whales there.
Wow.
Wonderful.
Yeah.
You are
It's a
blessed.
beautiful area. Yeah. Okay, so we're 10 people now. Okay, maybe let's just start. Everyone else who will jump into maybe in a minute or two. So last year we started with NextNess because we were very curious about how can we actually create materials or energy by not extracting materials from Earth. So we went from extraction to creation. And as we are all very deep into like technology things like exponentials and other things like energy, mobility, whatever, we thought about, okay, what is actually something that we are depending on, but we not really see as an, let's say, sustainable asset. And I was very interested into advanced materials and especially like sustainable materials. And that's how NextNess actually started pretty much. So what we looked up for was in our last conversation with Anne as well was can we actually create living materials that are self-healing, self-regulation, and self-replications. And today we thought about, okay, if we go one step further, we have to think about the next, let's say, 100,000 of years where we can produce energy in a very regenerative way. And that means that we don't extract things from the earth. So for example, oil, fossil fuels, currently like with materials that we use for solar production, and all those kind of things are not very sustainable in the long-term perspective. So we reached out to Anne again and said, hey, could we use your bacteria to produce energy in a very, or let's say in a more sustainable way? And that's how this topic is all about. So we want to talk about energy and clean energy especially. So how can we store energy, harvest energy, and more from like regenerative materials or bacteria. So I will take Anne in a moment, and a little housekeeping in the beginning is if you have questions, just ask them in the chat, and Stephanie is collect them, all of them, we curate them and then ask them later in the Q&A session. And maybe a small introduction of Anne. She's an associate professor of biology at the University of Rochester, received her PhD in biology from Stanford, and hope you will all enjoy her presentation. And I'm looking forward to having thriving Q&A after her talk. So here's Anne.
Great, thank you, Malta. Good morning or good afternoon to everyone. I'm here from icy, icy Rochester, New York, where literally everything is covered in ice. All right, let me pull up my slides. Okay, so today I'll be talking about how can we use synthetic biology for energy applications. And this is a really interesting talk for me because you know, there's so many different projects in my lab, and then I had an interesting talk with Malta and Thomas and Stephanie a week or two ago. You know, it really became clear to all of us how many projects you can align with energy applications in one way or the other. So I'm curious to see what you guys think about this, this framing. So in general, the main goal and vision of my lab is, can we use bacteria to make materials? Right, so we're looking to see if we can replace kind of traditional chemical factories with the biological factory in such a way that we can make materials that are really sustainable, sustainably produced, simple and inexpensive to produce, but that has the complexity and the value of traditional materials made by chemical approaches. So I mean, I think bacteria are fantastic for this application because, you know, our factories make themselves. So they're self-replicating factories. You know, you can grow up a liter of bacteria for just pennies, you know, worth of material to produce them. I think the real value is that bacteria are just fully sustainable, right? So the chemical reactions catalyzed by bacteria take place at, you know, room temperature, standard pressure, aqueous environments, typically without requiring or producing toxic chemical waste. You know, and when you think about material production, they can make materials, you know, for example, in comparison to laying down cement, you can make biological materials on bumpy surfaces, vertical surfaces. You can take bacteria with you, make materials on site, and they also work in microgravity environments, so you can make materials, for example, in space in the future. But in particular, can you make materials for energy applications? So, you know, I had a very interesting chat with the NextNess organizers around the ideas of, you know, how could bacteria be useful for harvesting sunlight? You know, like solar panels, harvesting kinetic energy, such as in wind turbines, for example, right? As well as for storing the energy that you would be harvesting. And so I think I have some interesting answers for all of these prompts, and let's go through my ideas. So first, you know, how can we use bacteria to harvest sunlight? So this is an idea that my lab's working on that I think is so interesting, and I'm really curious to see where it goes. So we got the idea, could we use bacteria to make a new version, an improved, sustainable version of microlenses? Right, so what are microlenses? They're just very tiny lenses, as the name suggests. They're really, you know, but they're really beyond what the name implies, the next generation, the future of optics and imaging and harvesting of sunlight. Right, they're what's used in solar panels to collect energy and so, you know, in solar harvesting. However, the current generation of microlenses, they're not truly on the micro scale. They're more like hundreds or possibly tens of micrometers. They're typically highly imperfect optical devices, and they take a lot of energy to produce. And actually solar panels, well, over their lifespan, harvest a lot of energy. It doesn't always even offset the energy required to produce them. So anything we can do to make microlenses less intensive to produce, as well as more desirable with their optical properties, the better for the overall efficiency and environmental friendliness of solar energy. So when I was thinking about this problem, how can we make microlenses using bacteria, I was inspired by a natural system, which is these amazing starfish called brittle stars. So brittle stars have been described as perfect optical systems because they literally cover their arms in glass, right? So they make bioglass, which is polymerized, silica or silicate, such that each, you see on the right-hand side, each cell is covered by a layer of glass, turning it into a little microlens, right? And so these little starfish microlenses are lightweight. They are better optical quality than man-made microlenses. And everything is produced just using the power of enzymes, right? So the enzymes make the glass coating. You don't need high temperatures, high pressures, that kind of thing. So how can we use that for bacteria? So could bacteria act as a microlens? If we got bacteria to coat themselves in bioglass, that could be something that would be, bacteria do it so it's less energy intensive, labor intensive for the humans. It'd be very sustainable, right? Because bacteria would do it at room temperature and in aqueous solutions. And technologically, I think the bacteria pose a great advantage because they're truly on the micron scale, right? So bacteria we work with are between 1 and 2 micrometers in length, and even less than a micrometer in width. So they'd be 10 to 100 times smaller than the current generation of microlenses. But we have to have our lenses be tough, like tough enough for applications, just physically. And ideally, you want to have uniform light focusing properties, right? So when we did some physics-based modeling for what would happen if we had bacteria coated in glass, so our predictions are that you would indeed have bacteria that could focus light. However, the bacteria we work with is shaped like a rod or like a tablet pill, right? So depending upon if it falls this way or that way, you get your light focused in different ways, right? So ideally what we want is bacteria coated in glass that's spherical. So no matter how it tumbles, you have the same light focusing properties. So what's our approach? So we have our favorite bacteria to work with in lab. It's, rod-shaped E. coli. And we make one change to it, which is we engineer this bacteria to express one single enzyme on the outer surface of itself, right? So this is the enzyme silicatine that is found in the starfish. It's also found in marine sponges. So these sponges, they make a skeleton out of glass to support themselves. So that's all just, all this polymerized bioglass is all the work of one single enzyme to express on the outside of the bacteria with the idea that it would now coat the bacteria in bioglass. So I won't give you all the gory details about our experiments, but through various chemical analyses, we have demonstrated that our bacteria are fully coated in polysilicate or bioglass. When they're coated, they're stiffer. So normal bacteria are a little bit spongy and squishy, right? But when we coat our bacteria, or when we have them coat themselves in bioglass, they're 4 times or more stiffer than uncoated bacteria. And we're able to also tune the shape, right? So on the bottom here, I'm showing you on the left the picture of just a regular shape, rod-shaped bacteria coated in glass. And then on the right, we can also engineer the bacteria to be more round. So this is like 95% spherical. So we're approaching, perfectly spherical lens as well. And we've shown that our bacteria can transmit light with, less than 0.1% backscatter. So this is the work very much in progress. It's, we have a second-year PhD student on the project, and we'd love to see if we can really turn this into like, kind of mass-produced, really sustainable microlens. So we imagine lots of amazing applications for these microlenses. So I think these would be perfect for collecting light in solar cells or solar panels, right? So when solar panels are collecting light, they have these, little photovoltaic areas that collect the light that are more or less the exact same dimensions as our bacteria, right? So we have more smaller bacteria, more smaller microlenses in our solar cells, then we can collect much more light per solar cell than we're doing currently. These microlenses, since they're smaller than the current generation, also gives a lot more options for lenses that are both flexible and thin. If you just coat your surface with these lenses, then it's flexible, on the order of micrometers instead of hundreds or tens of micrometers. Something that our physics modeling also indicates is that, if we have these bacteria coated in glass, then in principle, we should be able to use these as now bacterial lasers. So tiny lasers are the same size as bacteria. The idea is if we engineer them to produce fluorescent proteins, which is, very straightforward for synthetic biologists, then the glass coating around would act as like to make whispering gallery mode interactions with the light, so that we predict that we should be able to have our bacteria emit lasing light. So it's going to be amplified light with a narrow range of emissions, which I think is really interesting for various biological detection applications with really stronger signal. Smaller wavelength means you can have lots of different detection mechanisms going on at the same time. So I think that's a really interesting, hopefully glimpse into the future of optical imaging applications. Okay, so these are my lab's ideas for how we can harvest sunlight using synthetic biology. What can we do about harvesting kinetic energy? So, talking with Malta and Thomas and Stephanie, we were discussing, what can you do if you wanted to, for example, make wind turbines or, some device to capture wind energy or water energy in a way that's more sustainable than current practices. So my thoughts for that are, one of the best structural materials is found in nature. It's these seashells. So seashells are lined with a material called nacre. It's what's known as mother of pearl in many languages. Nacre is a really interesting material because chemically it's mostly the same as cement. So it's 95% crystallized calcium carbonate. But in comparison to cement, nacre is up to 1,000 times tougher and it's highly stiff. Right? So most materials are tough but not stiff, or stiff but not tough. But nacre is both tough and stiff. That means that if you put on it, it doesn't change shape. And if you try to bend it, it doesn't break. That's just what you want for something structural, right? That can withstand forces. So lots of different groups are trying to make versions of nacre using more traditional chemical approaches. Typically, these require, very high-tech machinery or instruments, or they make a lot of organic waste at the end, that's very expensive to get rid of. So our approach is, can we use biology to make nacre in a way that's sustainable and, very straightforward and inexpensive? So if anybody went to my talk, whenever it was, back in January, this is going in a different direction. So stay tuned. So, so this is what nacre looks like if you zoom into it on a nanoscale, actually. So this is the shell of a blue mussel that we've cracked in half, and you're looking at the cross section. So you see that the calcium carbonate is in these long, thin platelets, and the platelets are glued together by these polymers that are sticky and stretchy, right? So this kind of nanostructured composite material, the structuring is at the heart of its amazing toughness, because if you try to bend the material, the calcium carbonate doesn't bend, right? That's very stiff. But the polymers are squishy, so those deform, and that dissipates the mechanical energy you're putting into your material, right? So that prevents the whole structure from fracturing. So if you want to make something that resembles nacre using bacteria, we need to use bacteria to make cement, to make crystallized calcium carbonate, and we need to use bacteria to make some sort of tough, stretchy, sticky polymer. Right. So luckily, the lab very far. Thanks. Yeah, so there's a bacteria found in the wild that is incredibly useful for our purposes, because if you grow the bacteria, in your beaker, and you give it some urea, it'll break the urea down and raise the pH, and then that ends up promoting crystallization of calcium carbonate. So here's a picture of a layer of cement we were able to make in our beaker, where it's only just bacteria and urea and some calcium to make the calcium carbonate with. So in addition to the cement, we're also going to need some sort of robust polymer. So for this version of nacre that I'm talking about today, we're using a material called bacterial cellulose. So cellulose is, maybe you've heard of it, it's famous because it's a structural polymer found in plants, a lot of wood, a big fraction of wood is made of cellulose. What I'm showing you here is, this is what you get if you take kombucha and let it ferment on the bench top for longer than you would normally do that if you're going to drink it. So, so bacteria also make cellulose, in addition to plants and trees. So here's a specific kind of bacteria where the longer you grow it, you see on the top of our tube, there's this thick layer, and that's bacterial cellulose. So it's very easy to produce a large amount of cellulose. You just grow the bacteria in some tea, you brew some green tea, add the bacteria, let it sit and grow, and the longer you wait, the thicker and thicker this cellulose layer grows. So that's the polymer we're going to be harvesting to make our nacre with. So here's our approach. So we take that thick layer of cellulose. It's very inexpensive. We bought a kitchen blender. We throw it in the blender, blend it up. Then we put it in our flask and we mix it together with the bacteria. So over time, the bacteria is making the crystals of calcium carbonate that stick to the fibers of the cellulose that's in there. So we can let it start growing, start making crystals, then we put it into a mold. So whatever shape we want, we put it in a mold of that shape. And then it gets very stiff as the crystals develop, right? So we end up with, in this case, like a little tablet of stiff cellulose-based nacre. So what is it like? We were actually astonished. It performed much more than we had expected for its mechanical properties. So on the top here, I'm showing you Kui on the project made it into the molded shape of a bowl. And so he's able to take his bowl, turn it upside down and stand on it. So it's taking his full weight, the weight of one PhD student, without fracturing or cracking noticeably that we could find. On the bottom, he also made like a little tablet. I don't know, it's like 5 centimeters by 5 centimeters, more or less. And he took it up to the top of our building and dropped it off. So he dropped it from 10 meters in height. And you can see that on the top, that's when you only just have the calcium carbonate. Calcium carbonate by itself is very brittle, so it just explodes into powder. And on the bottom, that's when we had like the full thing. So we had the cellulose mineralized with the bacteria, and we don't see any visible changes after dropping from 10 meters. So it's very robust and resistant to fracture. And for us, it's exciting that it's also remoldable, right? So here we started with this funky kind of shell shape, our like nacre inspiration. So we molded it into a shell shape on the top there. And after it forms the shape and gets very rigid, we can soak it in water, put it through the blender again, and then remold it into all the different shapes that you see. So I like the fact that, we have kind of innovative end of life scenarios for this material, because when it's done with its primary purpose, you can just make it into whatever else you want for a new different purpose, as long as you want something stiff and tough. So I'm really excited about this moldable bacterial nacre because our previous nacre that we made was also very tough and stiff, but it was only just flat, right? And here's the way we can make something really structural, but with a shape. So I can imagine for harvesting kinetic energy, this could be a fantastic material to use to make the blades of your wind turbine, the blades of your water wheel, for example, if you're harvesting water energy. We also have various applications in mind, for example, for aerospace and naval components. So nacre is very lightweight considering how tough and stiff it is. So I think it's fantastic for vehicles where, the more lightweight the vehicle is, the less fuel you have to put into it to, travel a given distance. Natural nacre is fantastic because it's anti-fouling. That means that biofilm doesn't grow on it, fungus doesn't grow on it, barnacles don't grow on it. So this could be really interesting for various civil engineering purposes, for making buildings or statues or objects that are just exposed to the environment for long periods of time. Since all the materials we use are biocompatible, the cellulose is edible, the calcium carbonate is similar to what makes up your teeth and your bones. This could be really interesting for example, for making bone grafts or pins or something where, you know, you have something that's a support or a structural replacement for bones that can be left in indefinitely without having to have, you know, a surgery to remove the pin after your bone heals. You know, I love the idea that this could be something that you could make, for example, in a space colony, right? So if you want to make a moon habitat, right? Like, I don't think it's worth it to load your spaceship up with cinder blocks, because that's going to take a lot of jet fuel, rocket fuel to get off the ground. I think it costs, what is it, like $4,000 in rocket fuel to launch one lemon, like out of Earth's orbit. So instead of launching your cinder blocks out of Earth orbit, I propose you should just launch, you know, a very tiny tube of bacteria. And once you get to space, you can make your cellulose, you can use the regolith and harvest the calcium from that and make your structural material in that way. So that's our ideas for how you could use synthetic biology, biotechnology for harvesting kinetic energy. All right, so for the last part of the talk is, what could we do for energy storage questions, right? So this is an example where we were thinking of different applications for our new technology that we developed in lab. So my group is the first to develop 3D printers to print bacteria. The idea is that we're printing bio ink, if you want to call it. So we have our own homemade 3D printers that deposit ink, and the ink contains bacteria, such that after printing, the bacteria are enmeshed in this hydrogel that keeps them in place. But because the hydrogel is mostly water, then the bacteria can survive, they can make materials, they can eat and respire, and that kind of stuff, right? So we've had a couple of publications already applying our 3D printers for various kind of fundamental biology projects. Here's a new project where it's hopefully going to be accepted very soon, where we're using our 3D printer to print microalgae. So microalgae, they're like bacteria in the sense that they're single-celled organisms. They're like plants in the sense that they are photosynthetic, right? So we had the question, can we make 3D printed photosynthetic living materials using only microalgae in our 3D printers? So here's an example of the kind of materials we can make. So when we print a microalgae, we can print it like at a very small scale where the resolution is less than 1 millimeter. We can also use our newest generation of 3D printers that print at very large scales, so dozens of centimeters, in dimensions. What I love about these materials is that they're really, you know, in a certain sense, autonomous, right? So basically we take a layer of, you know, our favorite bacterial cellulose, like a nice robust substrate, we print the bacteria on it, and then you can just take your cellulose, put it just whatever on the bench top on some plastic, and over time you see that our material gets greener and greener, right? So our cellulose, it's photosynthesizing, it's surviving and growing even without, we don't have to feed it, right? All we do is we shine some light on it during the day, and then that's all we have to do to feed it. So it's able to grow without us providing it nutrients or sugar or anything like that. So how does it behave? So our photosynthetic living material is really interesting from a material standpoint as well, because here I'm showing it's reattachable. You can take it, kind of peel it off the cellulose, deposit it on a different piece of cellulose, and then it sticks, you know, quite well, so it doesn't fall off the new substrate. It's got really interesting robustness, right? So you can fold it, you can twist it, you can crush it. Then when you unfold it and untwist it and uncrush it, it looks the same as before. We've even done this, you know, if we let it sit out on the bench top for 28 days, it looks the same as on day 0. So I think it's got really good physical robustness as well as good biological robustness over time. And you know how our bacterial nacre was remoldable, this is regenerative, right? So here's an example. We took our 3D printers, we printed the letters BN, you know, for our department name, in microalgae. We grow it for a few days to get nice and green. Then we can recover the algae. So we can dissolve it, dissolve the letters. We grow the algae for a few days, and then we can 3D print and make 4 times as many letters as we started with, right? So this is really interesting because, you know, you can have kind of the tools in the hands of the people. You can print your living material, send it to the end user, send it to space, send it to somewhere else, right? And then the end user has everything they need to make more of the materials or to recycle or regenerate the materials at the end of this lifespan. So I think this is a really interesting potential approach for making, photosynthetic skin, making biogarments, right? I love the fact that these are, in one way of looking at artificial leaves, right? So this is basically like something that you can engineer and design to harvest sunlight and store as energy in the form of, biological energy, which is sugar. These are also really interesting membranes. For example, if you wanted to do some sort of filtering function in a sustainable way, this could be a good application as well. Okay. And I have one more example for what we can do to make energy storage applications happen with bacterial approaches, which is, can we make graphene using bacteria? So graphene is a really interesting material. It's the first two-dimensional material ever characterized. So it's just one single layer of carbon molecules. It's among the most conductive materials ever characterized. It's got one of the highest tensile strengths ever characterized, and it's very flexible, and it's got all sorts of amazing other properties as well. So if you have a very expensive clean room set of equipment, you can make, very pristine graphene in very small quantities, but which is very useful for some applications. I'm interested in, can we make large amounts of graphene in ways that are high quality and sustainable? Right now, the answer is no. Or before my lab stepped in, the answer was no. So here's like a typical approach for how you make large amounts of graphene. So basically you start with graphite, pencil lead, so to speak. You take your graphite, you oxidize it to graphene oxide, then you have very thin layers of graphene, but they're covered in oxygen molecules. And then you reduce it, and the more you can reduce it, the more graphene-like your material becomes, right? So this is the way to get, very thin layers of graphene that's almost pristine, so very few, side groups on it. The problem for us is that both of these steps are very energy intensive and produce a lot of chemical waste, right? And the second step, the reduced graphene, to make reduced graphene oxide, for example, one way you can do that is you heat it up to 1,000 degrees Celsius for 24 hours, which is not very energy efficient. So we look to see, can we take this second step and make reduced graphene oxide in a way that's much more sustainable? Right. So our approach is to use this amazing bacteria called Shionella. Shionella is really cool because, so how animals breathe oxygen, right? That means that when we're metabolizing our energy, we have an extra electron that we donate to oxygen. That's how we respire, right? So Shionella also respires, but it gives extra electron not to oxygen, but to inorganic solids. So it can reduce metals. This means that you find it in a lake attached to a rusty piece of metal that fell in, right? Because it breathes the metal. And what's so great is that, it can reduce these inorganic metals just on the benchtop room temperature in just a few hours, right? So here I'm showing you some tubes on the bottom. So the first tube is a black tube of graphite. Next to it is a brown tube of graphene oxide. And then if you take our brown graphene oxide, mix it with the bacteria, and just leave it on the benchtop overnight, then we get, in the green label there, the microbially reduced graphene oxide. You see it turn black. So just by sitting on the benchtop overnight, our bacteria could reduce the graphene oxide to graphene materials. And when we measure what's the conductive properties of these materials, is with this kind of graph we're showing here on the right side. So the slope of this curve, the steeper the slope is, the more conductance our material shows. You can see in orange that the graphene oxide is flat, it's not conductive, it's an insulator. But then you can see the blue and the green curves, have a high slope, right? And so in green, the microbially produced graphene is the same order of magnitude of conductance as in blue with a chemically produced graphene material. So we have quite good conductance with our microbial approach. And we have also distinct advantages from the chemical approach, which is that our bacterially produced graphene can be stored longer than the chemically produced graphene. So after 2 weeks, the chemically produced graphene is clumping together, which makes it less thin, less conductive. But ours, we don't see clumping after 2 weeks. Now ours is also thinner, which means that it's, more flexible as well. So yeah, I think it's pretty exciting that we're able to produce graphene materials using only bacteria and some graphite. And there's lots of interesting applications for this in the future, potentially, right? So this could be a really interesting way to make biosensors. So something, for example, like a sticker on your skin that's very thin and flexible, and is like stable over, time frame of weeks or months, that can, for example, detect like how much glucose is in your blood, right? We also didn't show today, but we have techniques where we can pattern the graphene. So for example, if you have your graphene flakes, you can have it be reduced on one side and not on the other, right? That makes it easy to self-assemble into composite materials. Or for example, you can print in high resolution. Since our graphene is conductive as well as very stable in water, could it be like the next generation of e-inks, like for your Kindle book reader? And of course for energy storage, right? So graphene is fantastic for possibly making supercapacitors that are smaller than before. So can you coat everything with our graphene to make it thinner, as well as can we produce batteries with with ultra high energy density that are transparent for the first time, which could be really interesting as well. So I'll wrap up here for today. So just to summarize, I think there's a lot of interesting kind of energy focused materials we can make with bacteria. So we made some really tough structural materials. We made some flexible living materials. We made graphene. We were working on making microlenses and lasers using only bacteria. And I didn't mention today, but we can also make magnetite using only bacteria as well, which is, got interesting magnetic properties as well as being very strong. So thanks everyone that is currently working on the projects, and as well as many people in the past have also worked together. And at this point, I'm happy to answer anyone's questions.
First of all, thank you very much for the presentation. Before we jump into like the more deeper question, I have a very basic question actually to like combine those things in general. Do you think it's possible to build like let's imagine in 10 years, 5 years, one household, a house in a suburban or somewhere? Do you think it's possible to use like microlenses, like what you just mentioned, to produce enough energy for one household?
That's a great question. I think that would be, so I guess I don't know like how much, I think it might depend upon how much sunlight your area of the world gets, right? But I can certainly see that this could be like the new way to harvest sunlight in solar panels, right? So, I think it would be, people already, are powering their entire household with solar panels, and this has the potential to make even more efficient energy capture.
Yep. But do you think it's also possible to store the energy like with microlenses, not with microlenses, but with living materials, and then harvesting the energy from the sun? So if this is possible with microlenses, so.
This was interesting. Yeah, could we combine our microlenses with our printed photosynthetic materials? I mean, certainly yes, I think as well.
Oh, interesting. Okay, let's jump into the question. Keith asked one thing, and he has this question probably for the last 10 years already in his mind. So here's the question. I'm just reading it. I've had the question for about 10 years about growing paper pulp or even low quality orientated wood fibers without nature in a tank. We could radically reduce rainforest loss when the market price meets the real price of high quality rainforest ecosystem. So his question is it biologically possible to create paper in a tank properly?
Yeah, that's probably really interesting question. So
thank you.
So bacterial cellulose, I mean, it's got a lot of paper-like qualities, right? So, you grow a thick layer, you dry it out, and that's the substrate on which we're doing our printing of the algae, for example, right? So this is a situation where it's really tough. It's you can crumple it and it doesn't tear, right? So you get a really robust material. One thing I'll say, I mean, there's two major differences that I can think of offhand, right? So one difference is that plants are attractive because they feed themselves, right? Whereas bacterial cellulose, we have to give it some sugar to eat. However, it's much more simple to harvest it, right? So with bacteria, you just lift it off the surface and dry it out, and that's your paper already. Whereas with plants, there's a lot of processing to go into it, right? I mean, the other major difference chemically is the fact that wood is a combination of cellulose and lignin, whereas the bacteria don't make the lignin, just the cellulose, right? Which actually confers, many advantages. I don't know if ZJ wants to say anything, but in the audience today, we have an expert on bacterial cellulose as well. If you wanted to say anything, but you don't have to.
I think you explained it very well. Yeah, the way you use it is like very, yeah, pretty much sums it up. Thanks.
But Keith, do you mention, or you meant just like creating paper pulp, or also like other materials made from wood, like glass, for example, could also be possible?
Yeah, so the challenge is always this question of, can you produce something at scale, enough of it so that the price equilibrium comes, so that you can stop destabilizing something that's higher value, in this case rainforest, or paper pulp, or whatever. There's a lab here at Uni that's working on photosynthesis, which is as direct energy source to electricity, and I don't know how they're doing. The question is, do we just go direct to producing electricity, because apparently photosynthesis from leaves is far more efficient than any photoelectric cell will ever be. And so, how do you go about it to make it, first of all, possible? I mean, that's the lab basis. And then how do you scale it?
Yeah, sure. Like another good feature of bacterial cellulose production is you don't need arable land. You just need like a bucket with tea in it, like some sugary tea, right? So that's something you can make, again, like on your moon colony, on your Mars colony, in your space station. You don't need to use your valuable pasture land. You can just grow it inside your factory, as long as you have, the only thing is you need a lot of surface area, right? So a lot of very like skinny vats all stacked up on top of each other, right?
I have like one thing to add, if I may. So I think like Anne just mentioned, it's like really cheap and you only need the surface. So in that case, for space applications, that's really cool because you have zero gravity and you can potentially produce a lot of surface for this kind of material to grow. So I think that's how you can actually naturally transform a 2D material into 3D structure, like just by playing with the physics around the environment.
Very interesting. Yeah, if you had like in space, like just the blob of water, could you have like a hollow sphere of cellulose? That would be very interesting, huh?
Interesting. Nicholas, you also had actually two questions. Would you like to ask the question directly to Anne, if you unmute yourself, please?
Yeah. So, sorry, just a second. I was just wondering with, I guess this was kind of before the presentation on making the glass coating on the bacterial cells. I just wonder if anyone has cultured the cells that are directly from the brittle star in vitro, just like outside of the organism. And I wonder, just like kind of thinking from a synthetic biology perspective, if there might be any advantages, like if it's a complex organism and you already know that that works in that organism, of using that for making the glass coating on the outside of a cell. And then you might have some use of having like a complex organism that already does that, and then tinkering with that afterwards.
Yeah, so to my knowledge, I don't know of anyone that has cultured brittle star cells in vitro. I mean, could be possible. I mean, I feel like I don't know if there's like a lot of brittle stars available. Like, I'm guessing you'd have to have like 10 kilograms of brittle stars and like try all different techniques before you got any cells that would work in vitro. And I don't know how many brittle stars you can get at a time to try that with. Certainly, you know, if you compare like the different properties of the natural organisms process with engineered organisms, so it's often the case that the natural organisms, so in this case, brittle star, they're often like more efficient at making the material. So they might make, you know, more glass more easily, right? But then on the other hand, they just make when and where and how much they want to, right? So the advantage of engineering bacteria to make the glass is that we have a lot more control over when and where and how much glass is it making, what shape is it making, and those kind of things, right? So, you know, if you want to really have control over these kind of properties, you have to be able to do genetic engineering on the organism. And I don't know what the tools are for doing that in brittle stars. We don't really have good tools for that right now. And one thing I'll say is cool with the brittle stars that I would love to recapitulate somehow in the bacteria, but we don't really know enough about yet, is that the brittle stars are cool because they can change the refractive index of their glass from day to night. What this means is that the glass coating on their arms is more or less reflective in day versus night. So in the daytime, they're brighter. So they blend in when the sun is shining, and at nighttime, they're darker. So, you know, they're more hidden from their predators and from their prey. And we don't really know how that happens. I don't know that it's been discovered how that happens in the brittle star, but it would be fantastic if we could have our bacteria also change their refractive index in different conditions. We'll have to work at that from the ground up.
Keith, you also asked again about the flexibility of macro. Actually, and you could talk about that as well, but we talked about that for in our last conversation as well. Maybe I can send you the link, Keith, but probably Anne, you could answer this question.
I can just say like in 2 sentences. So one thing I think is interesting about your question is that we've been inspired by also eggshells. So eggshells they don't have the amazing kind of nanostructure of nacre, but they have the same kind of constituent materials, right? So eggshells are calcium carbonate and polymers, just kind of mixed together more or less. So pretty similar to our, like the bowl that we made, right? Out of the cellulose and the calcium carbonate. And what's interesting is if you look at different species that produce eggs, right? So birds make eggs, their eggs are very stiff, right? And then reptiles also make eggs. They're also made of calcium carbonate and polymers, but they're much more flexible. It's not as stiff as the bird eggshells. And the major difference seems to be that the reptile eggshells have a higher ratio of polymer to calcium carbonate. The bird eggshells have more calcium carbonate to polymer. So yeah, like it would be great to start. Now that we have like our base proof of concept that we can make these stiff, tough materials, it'd be great to have a higher ratio of polymer and then have hopefully something more flexible that's still tough.
And Nicholas, you also asked something very interesting in my opinion, because I'm not 100% sure if your first question is also related to your second question, but like building a small biofactory for energy production. Is that something you meant with thermoelectrics, or am I wrong?
Yeah, so I don't know, I haven't like really thought this through, but I just remember reading a paper maybe like 10 years ago or something about using graphene as the conductor for I think at some point for transistors, and also for what are they called? I can't remember what the word is, but basically it's a material that gathers energy from the difference in heat on a hot side and a cold side. Yeah. And so basically they made this stuff they called power felt, which was a material where on you'd have like a situation with a that has heat on one side and cold on the other side, and taking advantage of the difference of those two, it would gather that energy and feed it through a circuit. Yeah, I just wonder if anyone is working on, or if anyone has thought about using the graphene that might be produced microbially for making that, just because this is kind of about making like this, it seems like this whole NextNess thing is about like sustainable energy harvesting. I just thought that would be like an interesting application. It's not really like a direct question. It was just like an idea I kind of was thinking of.
Yeah, sorry for the dog in the background. That sounds great. Yeah, I haven't thought about that experiment very much, but you know, if it's a graphene application, then in principle, it should be something we could do. Since we're a biolab, like right now our next step is making these biosensors that use field effect transisting. But yeah, I mean, that certainly sounds like something that people could also work with in the future. I know that we're negotiating at the moment to see if we can start working on this in collaboration with one of the government agencies here, and that might be more in line with what they're hoping to do with it, potentially.
In one of our conversations, and you also talked about building like a generator or using bacteria for magnification, or like a magnetic field somehow, right? This could also be very interesting to produce like energy on large scale, or like in a more larger way, right?
Yeah, I did not discuss, but yeah, we are also making magnetic materials with our bacteria. This was actually like we did our experiments only with space applications in mind. So we got some like simulated regoliths, like some fake moon dust and some fake Mars dust. And we used the same bacteria that we used to make the graphene. We mixed that with the regolith stimulant. And then what it does is it reduces the iron oxide to magnetite. So we kind of blend them up, we let it sit overnight at the bench top, then we passively extract. So basically you take your beaker and you put a big magnet on the bottom. And so you pull out all of the magnetic material, and then we can laser sinter that into this really tough, this like strong material that's magnetic. So yeah, this is kind of very like a zero effort, zero energy way, well, except for the sintering part, like an almost zero energy effort way to produce magnetic material just using like rusty dirt. So I'm sure you can also do this like not using regolith, but that would be like a next step for us.
And as we're talking about microlenses, do you think it's not only it's possible, but like replacing current companies with instead of traditional solar panels with microlenses? What do you think will be the next steps for like a company to replace their current manufacturing with microlenses made from bacteria?
Are you saying like how would people do that?
Yeah, probably. Is that like something you could implement it in your supply chain, or is there like a need for doing something very different in their group?
I mean, in principle, the microlenses are very similar to what's currently out there, right? So they're, you know, tiny little spheroids covered in glass, right? So I can imagine you could use it just very similar to how you would use the current microlenses. I mean, they're smaller, so potentially you might want to have higher positioning ability on them, right? So if you want to make sure your lens is like right over your photovoltaic cell, then that might need some sort of like, I don't know, some sort of like guide to position it. Because right now, like the lenses are like, like if here's your little photovoltaic cell, your lens is very wide, so it can kind of sit anywhere on it and still focus like some light. But with our micro lenses, they're like much similar in scale, so you want to have them kind of more of a match for how they line up. I can imagine that might be a difference.
Liam also had a very good question, because I had that also in mind when you talked about remoldable nacre. I probably, and everyone is talking about anti-fouling right now. We had that also in our last conversation. Liam, would you unmute yourself and ask the question, please?
Yeah. Okay. I think I can answer that. Yeah. So the question is mainly about the remoldability and what chemical exposure that is required for that. Mm-hmm. Since like anti-fouling is, you know, very valuable if you can actually have this stuff outdoors or in like a seawater environment where you have, you know, salts, you have biological material all floating together in a liquid. Is it still like resistant against those things? Mm-hmm. I don't know.
Yeah, so your question is interesting. I think in the chat you were asking about, is the cellulose still water soluble? And the great thing is that actually it's highly insoluble, right? So the bacterial cellulose, you see it floating on top of the water because it's, trying to avoid the water as much as it can. And so actually, this is actually a major problem. So people have tried many times, including our lab, have tried many times to mineralize cellulose, but it's very hard because you get this like really dense mesh of water insoluble polymer, and nothing penetrates it. All right, that's why in our approach we take our mat of cellulose, we put it in the blender, we blend it up to fragments, to shards, and then we mineralize that. Right, so it's not really soluble, it's just in little bits that are mixed in with the water, if that makes sense, right? Yeah, so after we make our final material, it's not water soluble at all. It's also like flame retardant, so we if you grab it with your pincher and hold it over a flame, like you can't set it on fire, which is not the most relevant for boat applications, but I think it is interesting in general. Yeah, so compared to like we have another way of making nacre where we have a polymer that's very soluble in water, and this is kind of the opposite approach. We have a very insoluble polymer. So yeah, I think it could be especially interesting for water vehicles.
Liam, I'm very curious about what you're actually working on. Do you want to talk about it for a second? Because we very much are curious about like, okay, what type of projects the audience is working on and finding ways to actually match them somehow. So if you want to, you could actually tell a little bit about your project or what you have in mind for ship coating.
All right, Melissa, you got me. I'm not a shipbuilder myself. I'm just a curious materials engineer. I understand the importance of anisotropy and the different effects of different chemicals, but I'm very much interested in seeing how the scale up of some of these materials could go in the future. And so I think especially some of these space applications are very exciting for future development, right?
But how did you come up with the idea of using it for the shipping industry, or especially like for seawater application?
Are you asking me or Liam, or both?
Liam, or both maybe, but especially Liam because he also.
Well, ships are exposed to harsh chemicals every day. I mean, where are we sourcing this calcium carbonate from? It's from sea life already, right? They already kind of do this naturally to like protect themselves from this environment. So to have our own vehicles that are present in those environments be resistant against those environments the same way that evolution has evolved to seems just to make sense. And yeah, like we can put the list of like properties that we can assign to it to say like, okay, this is the best solution to having a surface that is resistant, that will prevent our icebreakers from shattering apart from rust or breaking down, or having to use like anti-corrosive elements on the surfaces so we don't have our ships break down sooner than we need. All of those kinds of things. Those are all problems that I am aware of. I am not in a particular situation to solve them directly for you or solve them at the larger scales yet. But I'm curious to see how this stuff actually can be developed, outside of the lab. How do we get the nanoscale stuff to the large scale?
We have an agreement with a ship part manufacturer. They have this anti-fouling setup where we can send them our materials. And basically, they just kind of like dangle them off the edge of a dock into the water for a couple of weeks. So we're approaching the start of anti-fouling test season coming up in April. So we hope to get some results from that in the near future.
Okay.
Get to wait, all winter for the ice to go away before we can start the testing.
Right. Yeah. Eventually, we'll just be building our own Nautilus shells to swim out of. Right. Yeah, I don't have much else to add to this conversation. I'm not a synthetic biologist myself, but one of the areas I have worked in is nanoscale thin films coatings. So when you ask the question, how does the sea star change its refractive index? All you need to do to change your refractive index is change your interference material. So whether that's underneath the surface of your glass, changing it, the quantity of a liquid or a gas, so you have a larger change in refractive index, that'll change the amount of light that's going to be refracted out. And so that'll actually change how much reflection and absorption you're going to be getting across those surfaces. So maybe it has something to do with that, but that's just my hunch after 30 seconds of hearing about it.
So in principle, could it be changing not the glass, but like its skin under the glass and end up with a change in refractive index?
Yeah, you don't have to change the glass. It's like, I imagine chemically changing glass is an energy intensive process.
Yeah, I thought so too.
Exhaling gas might be a lot easier, something like that. Right? So just changing that, surface property of the skin itself is my best guess, but
that's pretty interesting.
Yeah.
It's a lot easier and doable.
Yeah. I mean, if they're doing this every night, I don't think they're regrowing their skin every single night. So yeah. I guess the last question that I sort of had was sort of similar to the one that Keith was saying earlier about wood fibers, but I'm coming at it from like the material science perspective, where it's more like, okay, how can you grow these things to have more anisotropic properties? Just because single cell bacteria kind of grow from like whatever start you have and just grow out. And in space, that's potentially every direction, right? So that's very exciting for like more growth. That's why we have like dishes in gravity that they can become little discs and stuff, right? So my question would be more like, here in the Bay Area, we have Impossible Foods, and they're trying to make a meat replacement, right? One of the biggest problems they have is their pea proteins and the other like the hemes and molecules that they use don't have larger scale structuring. So they don't grow long protein chains. So the kind of fibrousness that you have in like, say, a steak is not possible for them right now. And so like, how is it possible to kind of replicate some of those longer fibrous structures, like whether they're paper or whether they're, protein?
This is very interesting. So the first thing that this reminds me of is not based on the cellulose, but based on the calcium carbonate. So there was a paper that just came out last week in Advanced Materials. It's a group used a bit similar technique to us, where they're using bacteria to grow calcium carbonate crystals. And they're growing it, in our case, we grow it on top of cellulose. They were growing it on top of 3D printed, tough resin, right? So they they print their tough resin kind of in a cube shape, right? That's hollow in the middle. And then the bacteria will start growing the crystals, starting from the resin, so that it grows in and like covers up, or like fills in the gaps, makes it solid material. And what they would do was they had a version where they would 3D print basically like stripes of the resin, like parallel stripes, but then in each layer, the stripes would be rotated 60 degrees from the layer below. So that in each layer, the crystals were growing in a different orientation, right? And they found that when they did that, the overall material was much stronger than when every layer had the stripes in the same orientation. So I thought that was an interesting way. So basically they're like changing the orientation of the template to change the overall final crystal growth or in the crystal orientation. So that was fantastic, I think, for having control over larger order crystal orientation properties. The cellulose is trickier because it doesn't nucleate around the nucleation site like the crystals do, right? So we have to think more about how we could structure that, I think. Yeah, I mean, in general, anything that can self-assemble is very interesting, right? So we have seen that when you dry our cellulose, and everyone's cellulose, but we've seen it ourselves, right? If you take the big mat of cellulose and you dry it, and you look at the cross section, it spontaneously forms these kind of like stacked layers, like similar to actually what's in, you know, Meyer as well, right? So that's very interesting, right? But then, you know, that's only useful in the kind of this paper. I think part of why I think maybe the paper version of the cellulose is so tough, but we've not yet been able to replicate that in the mineralized material, because that's, you know, we blend it and you get it wet, then you mineralize that. So we've lost that structure at that point.
Does that actually play a role when we talk about photosynthesis of like living materials? What type of protein cells, or in general long protein cells? Is that something that's also important for like photosynthesis in living materials?
Not that I know of.
Okay. I was just curious if there may be like a cross or interdisciplinary field that could be interesting for living materials and the food industry. So
something interesting about the living materials that are photosynthetic, right? So they don't only harvest sunlight to make sugar, but they're also producing oxygen, right? Which I think is also interesting implications for, you know, anything that needs oxygen. In particular, like making the cellulose is interesting. Because for making cellulose, they really like to make it when they're exposed to oxygen, right? So it's pretty common that, you know, for example, if you have these bacteria that make the cellulose, so they're stuck inside a hydrogel, right? Then you only get the cellulose like around the edge of the gel, not in the middle, because there's not enough oxygen in the middle, right? So, you know, we had the question like, you know, what if we like 3D print together the algae that makes the oxygen together with the bacteria that makes the cellulose? Think we make cellulose like all the way through, right? So I can imagine if you like, potentially if you 3D structure where the oxygen is being produced, that could be a way to 3D structure where the cellulose ends up being made. But we'd have to actually try that and see what happens.
Let's try. Okay, to the audience, any questions about clean energy, or especially to add, or you want to talk about your own project to dig deeper into like clean energy things? If not, I'm glad that you all enjoyed this conversation with Anne. And if there are not any question further, we will do a stop here or break here. And yeah, that's it. You turned on your camera, so probably you have a question.
Yeah. Yes, that's it. I'm wondering whether it's maybe interesting for this circle to talk about our invention in wind energy. We are earning the wind energy with kites. Not today, of course, but maybe later on. And this is the matter. We reduce material by 90% with triple times of energy output.
So how does it work? So you have a kite, and then how do you harvest the energy?
We are doing the same like a kite surfer, but we change the kite surfer into an electrical locomotive on the train circle on ground. So it's going back and forth, and it's a production of energy. When an electrical train reduces its speed, then it produces energy. So that's the same recuperation process we are using for the harvesting of wind energy. And the second important point is we are doing it in a level between 300 and 500 meters. So the wind is much stronger and a lot more often. So we have a capacity factor of 75% compared to conventional wind turbines with 20%. It's a big difference. So next time, maybe if you're interested in, I can show you this idea, and especially it reduces dramatically the resources and the need of batteries. This is the most important part in the energy transition, because with the now existing renewable energies, it's so expensive because we need the storage technology for the 60 to 80% of storage. So it's maybe one of the ways to change the energy production.
But what are you currently using for producing the kite? Is it like a, yeah, let's say
I can show you some pictures if you're interested. Just a second. I have to close one of my windows here.
Because I'm curious how you actually harvest the energy from the wind. That's obvious, and I imagine they're like huge.
I show you a picture about it. Just a second. Yeah. So can you see it now? I would change the mode. Now, this is the problem of the energy itself, renewable energy, because of storage costs. The production costs are in not the, there's no big difference in the production costs. It's the green part of it, but the storage. I show you the pictures later, and this is how it works at the end. This is the impression of the landscape with conventional wind turbines. And what we are using is this idea. Maybe you've heard of vessels which are pulled by kites. So it is a simple step to remove the vessel, move the kite onto the ground, and connect it to a train with recuperation. The turbine which produces or generates electricity, and that's the idea behind. So we are assembling two well-known technologies. This kite, by the way, is producing 8 megawatts. 8 megawatt is one of the strongest wind turbines we have so far. And then we also use the bogie of an electrical train, and these together we are assembling on a closed loop, standard tracks, and going back and forth like windsurfers it does. And by the way, it's much better because this is one of the most important points here. The wind power density is going exponential by the level. And as you can see, the highest wind turbine is working in around 400 watt per square meter, and we are working in triple the time of it. And this is the impression. You can imagine how it works in the landscape. And this is a real zoom view. As you can see, is more or less nothing in the air. And you can imagine it. If you have you ever seen a glider in the air? And if you see it, how big is it? It's like a cent piece on the arm. So you have no disturbance in the landscape. So this is our test unit, and this is what I said already. The price level. This is the renewables are already competitive to the fossil fuels, but the problem is the storage costs. So that's it in short. And important is we have such a low cost of electricity that we are able to produce green hydrogen cheaper than gray hydrogen with it. You can imagine one of our 1 kilowatt hour from airborne wind energy costs around 1 to 2 cents, and you need 50 kilowatt to produce green hydrogen. So 50 times 1 to 2 is between 50 cents and 1 euro to get green hydrogen. And so you can solve also the problem for mobility energy and heating. We are still producing more than 80% of our energy from fossil fuels, and the most is coming from mobility, the mobility need and the heating need.
Okay, thanks a lot, Uwe. Probably we can talk more about that in another conversation. I'm very happy that you all enjoyed this talk, and if there are no questions further, I should thank you all for attending this talk, and I'm happy to see you in our next conversation. So, and thank you, Anne, again, and everyone else who attended. Let's, Uwe, could you add your screen sharing, please?
Yeah, I just try it. Just a second. Where is it? I'm not finding.
I can't end it. I don't know. Okay, anyways.
Just a second.
Okay. It's fine. I don't know how to do that.
It helps like this, or is the screen still available?
If you go to the very top of your
the,
screen, it should pop down the little red thing that says stop screen sharing.
I have only the mini pictures. I don't have the whole screen in the moment.
Well, Malta, you're the host. The people who participate, you should be able to usually end his screen sharing.
I tried,
Yes,
but,
but
anyway, just if you just can add this, this is all good. And no, Uwe, it doesn't matter. Thank you all.
I try my best.
It's all good. Okay, thanks again, and I'm going to end this right now. And yeah, so the next steps are I will send you all like a recorded conversation with Anne, and it will also invite all of you to a small research group where we talk about future energy or especially like clean energy things on web research within the next let's say 2 weeks, where we can just discuss like also like Uwe, your project probably with Anne and where this all fits together. Very happy to do that. And if there are any questions, just email me and we can discuss everything else in the next conversation. So thank you all again and goodbye.
Thank you. Goodbye.